Hi, I'm Daniel Chern from UNSW Sydney. Welcome to another adventure in pure mathematics. In this video, I want to tell you about an extremely important notion in algebraic geometry, the notion of a Cartier divisor. And in so doing, I'll also talk about its relationship of these types of divisors with the notion of invertible sheaves and hence line bundles as well. And that gives a wonderful way of going in between the notion of line bundles and also hence the study of maps into projective space and also of certain subvarieties of quasi-projective variety. Okay, so let me introduce the dictionary that I want to set up here, which will explain how this concept works. Okay, so our starting point will be X is some normal quasi-projective variety. So we need the notion of normality here because we want to talk about the degree of zeros and poles. Okay, so this is something that we will require. Okay, so that's the first thing to start off with. And we also remember that any invertible sheaf can be embedded as a subsheaf of the following sheaf script k, and that's the sheaf such that on every open set it's just going to be equal to the space of rational functions on X. Okay, so it's the constant sheaf because on every open set it's the same. Okay, so what is this dictionary? Okay, so what we're going to do is we're going to try to construct two maps that go in kind of opposite directions, not defined in exactly the same places, but it goes as follows. We start with some sort of a divisor. Okay, so this will be a value divisor, say D here, and we're going to associate it to it some sort of coherent subsheaf of this sheaf K of rational functions. It's going to be denoted OXD like that. Now inside this set of coherent subsheaves, okay, you can just select the ones which are invertible. Okay, so the ones which are invertible, basically that means they're locally free of rank 1. Okay, so we look inside there. And suppose we pick such an L, what I'm going to attach to that is going to be a divisor called C1L. This is C1 refers to the first Chern class. And as its name suggests, there are higher Chern classes as well. But for line bundles, this is the one that is of interest. Okay. So you have these two maps, and the first thing is they're both injective, and they kind of go in opposite directions, okay, up to this change of the codomain of this one with the domain of this one, okay? And the thing also is that if you start here and you go around this way, you start with an invertible subsheaf of K, you look at its divisor and then construct the corresponding coherent subsheaf of K, you get back to where you started. So in other words, if you have L, you look at its first Chern class, that divisor, okay, and look at OX, this corresponding coherent subsheaf of script K, you'll get back the original invertible subsheaf L, okay? So let's construct these two maps. So let's look at the first one where you want to start off with some divisor D inside X. So what's OXD? Okay, so it's going to be a subsheaf of this. So I just have to tell you which F lies inside here, so to speak, on any particular open set. And it's given rather loosely by this inequality here. Okay, you look at all these rational functions whose essentially whose poles and zeros, so you look at divisor of F, satisfies this here. Okay, when you add this divisor of F to this D, to this divisor here, it's effective. Okay, so it's a non-negative integer linear combination of prime or irreducible divisors. Okay, so basically this is controlling how bad can the poles be, okay, or must you have certain zeros inside there. Okay, so I think probably if you see a little example, you'll see that this is not such a difficult concept. And in fact, we've seen an example before, but let me try to go through it from this more general sort of a setup. Okay, so suppose now we look at our quasi-projective variety here is just P1, which we can always write as the union of these two affine lines, A1 with variable Z, and also on the other patch, A1 with the variable Z inverse. And we'll pick one colon 0 is going to be our point here, so that corresponds to a prime divisor on this P1. Okay, so that's basically Z equals 0 here. Okay, and so we can look at a divisor as just a linear combination of this case of points, okay, an integer linear combination of points, so we can look at n times this P. and we can consider what is this ONP. And we've seen what this is before, but let's see that this definition produces that same answer that we saw before. So what does this ONP mean? So if you look in here, what does it say? So here you've got NP, so that means that if you add NP to the divisor of f, okay, so you have some rational function whose divisor is such that if you add NP to it, it's going to be greater than or equal to 0. So let's just think for a moment that n is going to be something positive, okay? So if n is something positive, that means that, well, if you're away from p, this basically means that you have to be regular there, you're not allowed any poles. But if you are at p, then you're allowed to have poles as long as they get cancelled by this np, okay? So that means you can have poles up to order n, okay? Because if it's up to order n, then the most negative you can have for the coefficient of p here is minus n, and when you add that to this np, that'll still be non-negative. Okay, so you can have poles of order up to n at p, and everywhere else it has to be regular. Okay, so this of course has to be interpreted on each and every open set, and of course the way we've set things up, you only have to look at the affine patches here. Okay, so let's look at A1Z and A1Z inverse and what does that mean. So of course you're looking at rational functions, so you're just looking at rational functions in one variable z here. Okay, so what you're allowed is you're allowed to have a pole of order up to n at z equals 0. So that means that you have any rational function of this form, z to the minus n times some polynomial. Okay, so it's anything such that, well, if you multiply by z to the n, it has to be a polynomial. Okay, so that's anything of this form. Okay, they're the rational functions, okay, which have a pole of order at most n at z equals 0 and is regular everywhere else. Okay, so what about A1Z inverse? Well, this is no condition on A1Z inverse, because in A1Z inverse, this point is outside that patch. So there's no condition corresponding to that point. Okay, so it just means here that this divisor of f is greater than or equal to 0. Okay, np is not living there, so basically it's just divisor of f is greater than or equal to 0. In other words, it's regular, and being regular means that, well, what's the ring of regular functions on this patch? Okay, it's the patch of a1 with the variable z inverse, so it's just the polynomials in z inverse. Okay, so that's an example of an invertible subsheaf of k. That's this ONP. Okay, and that's something that we've seen before. Okay, great. So I hope that gives you a little bit of feel of what it means to give you this map here. Okay, so I've associated to this divisor something like this here, a invertible subsheaf of this script k. Okay, an invertible subsheaf of rational functions. Okay, let's go in the other direction. We're going to start with an invertible subsheaf L inside k. And the first thing to realize is that, what does that mean? That means locally it's going to be free of rank 1. So that means that you can find some affine open cover. Let's call that x equals the union of these ui's. Such this L, if you look at this on this ui, right, it'll be given by some Ri module. And it's basically going to be free of rank 1. So there's a generator Fi. So we can write this as Fi times Ri, and since this is a subsheaf of this script k, this Fi is going to be inside this this space of rational functions. So Fi is going to be some rational function. Okay, so to find this invertible subsheaf, provided you go to some fine enough open cover, okay, you can always write it as this form. Okay, it's defined on each ui as just Fi times Ri. So that's rather nice that you have this simple description. Okay, so with such data for such an L, we want to construct a divisor. So what's that going to be? And basically, this is essentially the thing we've been looking at. We just look at the poles and zeros of all these Fs. Okay, so let me make that all precise. And to do that, we need to be a little bit careful because, remember you have a sheaf here, so you can restrict to ui, okay, and we've said what they all are, okay. But also you can restrict to ui intersect uj, okay. So L restricted to ui intersect uj, you get by basically restricting either fi-ri or fj-rj. Okay, so what that means is that you can think of fi and fj both, you restrict them to functions on ui intersect uj, and on this smaller domain here, okay, so in the ring of regular functions on here, what you'll find that they differ by units. Okay, when I say differ by units, that means the quotient between them is a unit on here. And if it's a unit, that means it's neither, it has no zeros or poles. Okay, so that means that if you look at the divisor inside this intersection of the quotient fi and fj, that divisor is 0. Okay, so that's another way to think of it. Or another way to think of this is, so divisor on this intersection, fi, is the same. The divisor of fi is equal to the divisor of fj, because remember this is additive, so this is the divisor of fi minus the divisor of fj. Okay, so you have this equality, not everywhere, but on the intersection you have that equality. Okay, so what are we going to define C1 of L to be? Okay, it's going to be some divisor, so it's just some integer linear combination of divisors. So I just have to tell you, for any prime divisor or irreducible divisor D, what's its coefficient ND? And the ND that we're going to pick is just going to be, you just look at the valuation, okay, the order of the 0 of Fi. Okay, so it's just the order of the actually here I guess you want to look at the order of the pole. Okay, so the way I'll do it here is that it will be the order of the pole. So maybe I should put a negative sign to keep with my conventions that I had before. So maybe I'll put the negative here. Okay, so yeah, so this will be the order of the pole. The coefficient of D will be the minus ND, and that will be the order of the pole. So maybe a better way to write that, we put the minus here, okay? So it's the order of the pole of Fi at D, and that's for any Fi such that Ui intersect at D is non-empty, okay? And the point is if that D intersects two different ones, so how do you know that it doesn't depend on which index I? Well, if you have a different Fj that also intersects D, then those two will intersect in some place, so the two divisors of that intersection will be the same, and hence on that D you'll get the same thing. Okay, so that's why you can do that. Okay, and that means that this is well defined. Okay, this is now the definition of the first Chern class of this invertible subsheaf of script K. Okay, and one of the things that we can see very clearly is that in the case where you look at this first Chern class of this L, okay, what you can do is you can take this and you can restrict all these prime divisors to some particular patch UI. Okay, let's suppose you do that. So some of them might not live in UI, in which case they'll just go to 0, you just forget about them. But others, you replace them with that open set, okay, which is now a divisor on UI as opposed to divisor on the original X. Okay, and if you do that, what do you get? Okay, so you'll get these coefficients, and basically that's just a divisor on UI of this Fi. Okay, as a divisor on UI. Okay, so if that's started to get a bit abstract, let's just look at a simple example and see what happens here. Okay, so if we try to go back, and hopefully you'll see that when I do this example here, you'll see in what sense these are inverses. Okay, and see in this example how this equality holds here. So you do have, when you go around this way, the identity. Okay, so here you have an invertible subsheaf of script K. Okay, it's given on A1Z by this Z to the minus n K of Z, and here by K of Z inverse. And note that to describe them, okay, we use the rings of regular functions on each of them. So there's K of Z here and K of Z inverse, and we need to find these FIs. And the FIs here in this case are just Z to the minus n and just 1. And note that, well, the quotient of these two, that'll be either Z to the minus n or Z to the n. Okay, that's a unit on the intersection. Okay, so Z and hence Z to the n or Z to the minus n is a unit when you're looking at the intersection, so where Z is non-zero and Z is not infinity. Okay, that's the intersection of these two patches. Okay, so that's going to be when you remove 0. Okay, that's the only place where Z could be 0, and also it's the only pole of Z inverse, and you've also removed infinity as well. Okay. So they're the two things that you can do, and now what you can do is you can say, well, what is the divisor on this A1Z? Well, what you do is you just look at the poles and zeros here, okay, of this. So the poles and zeros here are going to be given by, on this A1Z, there's a pole at Z equals 0, and that's of order n. So that's why you have np, that's the coefficient of p here. Okay, there are no other zeros or poles inside here, okay? Okay, there'll be zeros if you go to infinity, but since we're only working on this patch here, okay, this doesn't tell you anything about what's happening at infinity, okay, when you look at the first Chern class, okay, we don't look there, but if you're on A1Z, you know what it looks like, okay, it's just np. Okay, so now let's look at and see what's the coefficient of infinity, okay, the point at infinity. Well, in this case, you have 1 is your function here, so on this patch here, okay, you're just looking at the divisor of 1, and of course that's 0. So away from your p here, okay, so that's this patch here, you've got 0, and that's what you find. Okay, so the first Chern class of this line bundle here is just np. Okay, and it's pretty easy to see from this example why, in general, okay, when you go around this way, you get back to where you started. Okay, so that's rather nice. But actually, you can say even more about what's going on. Okay, firstly, in general, when you apply this construction, you might not always get an invertible subsheaf of script k. Okay, that's the first thing. So, so that means that there are some divisors which aren't first Chern classes of some invertible subsheaf of k, right? They're not first Chern classes of invertible sheaves. Okay. So the ones which do arise this way, they're what are called Cartier divisors. Okay, so that's the reason why they're important. Okay, this notion of Cartier divisors, they're the ones that essentially are intimately related to invertible sheaves. Okay, because they arise in this way. Okay. So we can say more about this, and the reason why is that if you look on this side, okay, this is an abelian group. It's just the free abelian group generated by prime divisors. And it turns out that over here, you've also got some group structure. And so the map from L to the first Chern class is actually a group homomorphism. Okay, so let me first explain what is the group structure on this side, and then you'll see fairly clearly that it has to be a group homomorphism. Okay, so that will tell us even more information and make the relationship between these notions even stronger. Okay, so what is the group structure here? So suppose you have two elements, L and L prime. They're both invertible subsheaves of this script k. So invertible subsheaves of rational functions. Okay, and we may as well assume that we've made this affine cover, okay, sufficiently fine that they become free of rank 1 on that affine cover. So let's suppose L is given by these FIs. Okay, so it's basically FIRI as a submodule of this module of rational functions, and the L prime is given by FI primes. Okay. So what you want to do now is you want to say that I can construct an L times L prime. And the point is that these are both subsets of this K, so you can multiply them together. These are in fact what are called essentially analogues of fractional ideals. Okay, so they're not quite ideals because they might not live inside the structure sheaf, but they are submodules of this. Okay, so you can just multiply. So in other words, look at sums of products of elements. But in this case, it's quite simple, okay, because L on UI is just FIRI, and L prime is just FI prime RI. So if you multiply things from here with things from here, what types of things do you get? You just get things of the form FI times FI prime RI. Okay, any multiple of FI prime. Okay. Once you have that, that tells you what this L times L prime is in each of these UIs. Okay, and since it's a subset of this, and it's pretty easy to see that everything glues together correctly, okay, because the FI and FI prime differ by units on the intersection, UI intersect, the FI and FJ differ by units on the intersection of two things, and the same for the FI primes and FJ primes, okay, they'll differ by a unit. So you will have the condition, basically, there's descent data, the co-cycle condition for descent data will be satisfied by these. Okay, so this will actually give you an invertible subsheaf of script K. Okay, so certainly it's you can see from this is it's free of rank 1 if it is actually a subsheaf. And now we can go ahead using this description to compute what is its first Chern class. Okay, so what's its first Chern class? Well, just on UI, it's just going to be you just take the divisor of this, which is, since the divisor is a group homomorphism, the sum of the divisor of Fi and the sum of the divisor of Fi prime. So the sum of the divisor of Fi gives you the first Chern class of L on UI, and the divisor of Fi prime gives you the divisor of L prime on UI. So this is just the first Chern class of L plus this first Chern class of L prime. So that's rather nice that actually you have, moreover, a group structure here. Okay, and it turns out to be an additive group structure, of course. It's just products. You're looking at products here, right? It's an abelian group structure, rather, but usually written multiplicative because you're multiplying ideals, essentially, fractional ideals, and that multiplication gets carried over to the sum here. Okay, we'll talk more about the group structure here. That's very interesting in the next video when we look at tensor products of sheaves. Okay, and that gives a different interpretation of what goes on. One very natural question which arises are which of the divisors are actually Cartier divisors? And in general, this may not be such a simple question, but we have this wonderful theorem which says that if you're in the case where this quasi-projective variety X is smooth, then in fact every divisor is a Cartier divisor. So the key thing to show here is that every prime divisor is locally a principal divisor in the sense that it's given by the zeros of a single equation. Okay, so that's the key point here, and it uses the fact that if you look at those regular the ring of regular functions on X locally at any particular point, all those local rings, it's actually a unique factorization domain. Okay, so to finish off this video, I want to tell you this wonderful relationship between sections of invertible sheaves and also divisors, and this is kind of key to the setup of basic algebraic geometry. It takes a little while to get used to, but it's very, very important. Okay, so suppose you have some invertible sheaf L on X. Remember, every such invertible sheaf is isomorphic to an invertible subsheaf of rational functions. But let's put that aside for a little while. Okay, what I want to do now is I want to say there's actually an action of a group on this global sections of this L. Okay, so remember, if you have the global sections, there are lots of ways to look at that. That's basically this what are the sections over the whole of X. Okay, so this is a sheaf. So in particular, on each open set, it gives you an abelian group. Okay, so that's this one here. But we can also think of them as just sheaf homomorphisms from O to that L. So suppose you have some S like this. And the group that acts on it is just going to be the units in this ring here, H0x of OX. Okay, so a way to think of what this is, okay, is that, or what's the global sections of OX? They're basically just sheaf homomorphism O to O like this. And so the units inside here are just the sheaf isomorphisms from O to O, okay? And they're given like that. And the key point is that, well, if you have a sheaf homomorphism S from O to L and one from O to O, you can compose them, and that gives you a new sheaf homomorphism from O to L. In other words, a new global section. I'll call that lambda dot S like that. Okay, and it's quite easy to see, of course, this gives an action of this group on here. Okay, so since you have this group, okay, so this would actually be a vector space over the ground field K. Okay, so this is you have this group here, and you can look at the orbits under this group action here. And the set of these orbits is actually in bijection with a set of divisors D on X which satisfy the first following property. Okay, so they depend on the L. How? They depend on the L since O of D, this associated coherent sheaf here, is actually isomorphic to L. So this D will actually be a Cartier divisor. Right. Okay, so that's the first thing that you have. And the next thing that you have is that this D is greater than or equal to 0. Okay, so that's something that you'll find. Okay, so this is actually a wonderful result. Okay, and it gives you, you can use it in various ways. So one way to think about this is that, well, how do you imagine these sections of this line bundle? Okay, can you really imagine them in this sort of geometrically? Okay, how do you imagine them? Well, this actually gives you a way to imagine these geometrically, because you can now associate to them something which is actually just some divisor. So it's basically a linear combination of codimension 1 varieties inside X. So you can imagine them. And essentially the way you should think of this is that it sends a section to its zeros. Okay, so that's essentially how this bijection, this map here works. Okay, so I won't go through the proof of this theorem, but let me state more precisely what this map is. Okay, and we've seen some of these ideas before. Okay, in a previous video in this playlist. Okay, so here you have a section from O to L. Okay, and you can compose it with something like this if you like, and it's not going to change what's going to happen here. Okay, and then what you'll see is that, well, if you have this map from O to L, you can look at the generic point. Okay, and if you look at the generic point, you'll get O is this K, and then you can have this this L becomes this L eta, and of course these are isomorphic, and in fact this S, when you localize that will give you the isomorphism. Okay, so you have a map like this. And so the key point is that, well, this bottom map is an isomorphism, so you remember this section basically allows you to lift this map from O to K to L to K, because you can go now from L, that naturally embeds in its fractions here, modulo fractions here, and this gives you an isomorphism, so you come back this way. So you have a map from L to here, and the image of this L is going to be this OD. Okay, so that's the image of it. So you can factorize this, so this is OD is just a sub sheaf of this, so this is the inclusion map here, and it's basically the image when you go around this way, that gives you the OD. So that's the map that's involved here. You start with this section S here, okay? You form this diagram that you have here, and the image of L inside here, that's going to be some sheaf that's, well, it's going to be injective, because this is just inclusion into its modular fractions, and this is an isomorphism. Okay, so this is going to be an isomorphism here. So let me emphasize it's an isomorphism. Okay, so that's why the D that you'll get over here is isomorphic to L. Okay, so that's what you have there. And also this D, well, O maps into it, so that kind of tells you that it has to be effective as well. Okay, that's the reason why you have effectivity in this case. Okay, and when you think about it, what this is S, so basically this will be, when you interpret it like this, it's going to be an isomorphism. This since it's an isomorphism here, okay. S also will be isomorphism everywhere except for where on the support of D. Okay, so wherever the divisors which make up D are. Okay, and if you think about it, of course, in those places, okay, it's not going to be the whole of this O is not going to be the whole of OD. So this section basically that's telling you the zeros. So the way to think about this is you take a section, and if you interpret it in this sort of way, what are the zeros of that section? Okay, then that will give you this this divisor over here. Okay, and that's a great way to sort of understand what these sections are. You may think that, well, if you're just looking at the zeros, you'll lose a bit of information, and this theorem is telling you exactly how much information you're losing. Okay, because the zeros will only tell you what the section is up to this group action. Now, if X happens to be projective, actually this is just going to be the non-zero scalars inside K. So you're not too far off in this case. Okay, so that's rather nice. What this this sort of result sort of tells you is that one thing that's very important for you to look at is the condition for when are invertible sheaves of this form isomorphic. Okay, so we're going to make that into a definition, and this is going to be something that's very, very important in algebraic geometry. If you have two divisors d prime inside d of x, it doesn't matter whether they rise in this situation or not. Okay, they're said to be linearly equivalent if either of the following two equivalent conditions hold. The first one is that the corresponding coherent subsheaves d and d prime are such that they're isomorphic. OD is isomorphic to OD prime. And the second one, I guess maybe I should put here Cartier divisors. I guess no. Maybe I'll just leave out that it there. That's fine. You don't have to have Cartier divisors there. If this is isomorphic, and the other thing is that the more traditional sort of definition of what this is that if you look at D and D prime, these two divisors, okay, and you look at their difference, that's going to be the divisor of some f, where this f is inside some rational function. Okay, so let me just do the equivalence, at least in the case where this is a Cartier divisor. This is, I guess, the best time to do note this. Suppose this OD is a Cartier divisor, so on UI it's given by FI, RI. Okay, so the UIs here will be some, as usual, some open affine cover. Okay, and RI is going to be the ring of regular functions there. And let's suppose these UIs are fine enough, so this is locally free of rank 1. In fact, it's free of rank 1 here, so it's FI, RI. Okay, so this is going to be a subsheaf here. And one easy way to get something that's isomorphic subsheaf is that you just apply some sort of automorphism of this. So you just can multiply inside here by some f. Okay, if you multiply by that f, that will send any subsheaf of this to some other subsheaf. Okay, but the inverse will be multiplied by f inverse. So if you multiply all of these f's, you get f times fi, ri. Okay, and of course that's going to be another subsheaf of this form. Okay, so that's how you get this situation here. If you look at this, okay, what is the divisor of this here now? The divisor of this will be the original D plus the divisor of f. Okay, so that means that if you have something of this form, okay, you'll get something that's isomorphic. You'll get an OD prime that's isomorphic. Okay, and conversely, every such isomorphism, if you have two isomorphisms, right, you can look at the generic point, and that will essentially give you some isomorphism on this K. So that will give you that, and this is something that I guess we've talked a little bit about before in a previous video in this playlist. If you have something isomorphic, then the only way you can get that is if you've multiplied all of these FIRIs by some f. This f is independent of which patch you're looking at. Okay, and that gives you the opposite direction as well. And that gives you the very, very intimate relationship between studying sections on a line bundle or invertible sheaf on X and divisors. And it tells you why divisors are so useful in giving a way to understand and also to visualize sections of a line bundle, and hence also morphisms into projective space. I hope you enjoyed this adventure in pure mathematics.